Hi, so today I'm going to work through with you looking at probability distributions. So a probability distribution is simply a way of describing the probability of all the outcomes of a random event. We are looking specifically at discrete random variables, so that effectively means something that can only take certain values. So it might be the probability of rolling a particular number on a biased dice. It might be looking at the outcome on a spinner, something like that. I'm just going to quickly at first talk you through how we write probability. So we always use capital letters to denote what a variable is, and then a lowercase to describe when we're taking a particular value. So for example, I might say that x is the score achieved on a particular spinner. And if I wanted to know when x is equal to a particular value, I'd write it like this. So this denotes the value that the variable x takes in this case. So we can either do a table of probabilities, and I've given you an example in the PowerPoint. Hopefully you're following on, so hopefully you're on slide number 2 now. So I've given you an example of what the table of probability looks like. So in the top row, you've got lowercase x to denote the value that the variable is taking, and underneath what we have is the probability that x is taking. Because we are dealing with discrete random variables, the only outcomes that can happen are the ones given to you in the table, so therefore they must add up to 1, because we know that probabilities in the whole must add up to 1. So they might ask you for a table, or they might ask you for a probability mass function. So I've given you another example there. So it lists the probabilities and next to it the outcomes that take those probabilities. So rather than me drawing out an example on here that is literally exactly the same as what I've written in on the PowerPoint, I'm just going to go straight onto the examples that I've actually selected to go through in the book. So I'm going to go through example number 1 from my PowerPoint, which is on slide 3. So example number 1. So 3 fair coins are tossed. Write down all possible outcomes when the 3 coins are tossed. So whenever we're asked to write outcomes, we should try and do them in a really logical manner. So when I'm tossing a coin, I'm only going to be able to get heads or tails. I'm not going to be able to get anything else. We are assuming that the probability of it landing on its side is so small or negligible that it's not something we're considering. So we're only looking at heads or tails. So I could get 3 heads. I can also get 2 heads and a tail, but I've got multiple ways in which 2 heads and a tail could happen. So I have got to consider all those outcomes because it could be you've got the chance of getting it on each of the coins. So you do have to consider all options and what coin we're talking about. So you might have coin 1, coin 2 and coin 3 because they are separate ideas. So I could have 2 tails and a head, but I've got 3 different ways in which that could happen. Okay, and then I could also have 3 tails. So I've got 1, 2, 3, 4, 5, 6, 7, 8 different outcomes that I could have. So part B, a random variable x is defined as the number of heads when 3 coins are tossed. Write down the probability distribution of x as a table and as a probability mass function. So, first of all, I need to differentiate my outcomes. So I've got 3 heads here. In each of these 3 cases, I have 2 heads. In each of these 3 cases, I have 1 head. And in this case, I have no heads. So they're the only possible outcomes. So if I was to draw my table, so mine will be a sketch of a table. I know a lot of you like to use a ruler when you're doing these, but it really isn't necessary. So this is part B, I, doing it as a table. So on the top I've got x, so I'm using lowercase x to denote a particular example of that variable. And then underneath I've got the probability when the variable x is equal to this particular value. So I've got 0, 1, 2, 3 heads. So this, we're going back to probability basics. Probability of getting a heads is a half, and the probability of getting tails is a half. So the probability of getting 3 tails, which I could also say is the probability of getting 0 heads, which I'm going to write as x is equal to 0. So this is what we would really need. It's just this is how we might write it to start with when we're translating the question into our own, into our heads. Is going to be a half times a half times a half, which is a half cubed. So a half cubed is 1/8. So the probability of getting 1 head, or the probability that x is equal to 1, well, because they're the same probability, that's still going to be a half times a half times a half, so it's still going to be a half cubed, but I've got that same thing 3 different times. So it's 3 times by a half cubed. And a half cubed is 8, it's 1/8, so 3 times a half cubed will be 3/8. So now I want the probability that x is equal to 2, so that means having 2 heads occur, which will again be 3 times a half cubed, which is 3/8. And then the probability that we get 3 heads, there's only one option, which is a half times a half times a half, which is 1/8. So 1, 2, 3, 4, 5, 6, 7, 8, that adds up to 1 whole. Perfect. For part B, part 2, where it wants it as a probability mass function, so we say the probability when x is equal to a particular value of x, and we use set notation. First of all, we give the probabilities. So the different probabilities are 1/8 and 3/8. Next to 1/8, I can say x is equal to 0 and x is equal to 3. So what this means is that when the variable has an outcome of 0 or 3, so 0 heads or 3 heads, the probability of that occurring is 1/8. And here, the probability of getting 1 head or 2 heads is 3/8. Sometimes you might say to the side, otherwise it equals 0, but they don't always expect that. What we can assume here is, if I didn't write this, is that these are the only possible outcomes in this particular question. So that's not always needed, but occasionally they do show that in an exam question. So it's worth recognising what the notation means in any case. Okay, so I'm going to go on to example number 2. So this is still on our slide number 3. So a biased 4-sided dice with faces numbered 1, 2, 3 and 4 is rolled. The number on the bottommost face is modelled as a random variable So I'm just going to write that down. I always think it's useful to write down what my variable is talking about. So given that the probability that x is equal to a particular value is k over x, find the value of k. So k in this case is going to be a constant. Well, I've got quite a bit of information that I can use that maybe isn't given in the question, but I just know. I know the sum of all of the probabilities is equal to 1. So if you haven't seen that notation before, that capital sigma does mean sum of. So the sum of all the probability values must be equal to 1. I also know that x can take the values of 1, 2, 3 and 4. So I'm just going to do a rough probability table to work out my value of k. So the probability that x is equal to 1 is k over 1. Because we know the probability of each one is k over x. Obviously we can simplify that later. Therefore the probability that x is equal to 2 must be k over 2. That it's equal to 3 is k over 3. And that it's equal to 4 is k over 4. Well, I know that k plus k over 2 plus k over 3 plus k over 4 must be equal to 1 whole. So what I would do, you can either make these a common denominator, so it would be 12, add them together and multiply, or we can just multiply by each denominator to get rid of it. You can always multiply by the largest denominator to make that clear, but sometimes people find that a bit more difficult, so I'm going to just do it slightly step by step. So I'm going to get rid of this times by 2 first. So I need to multiply everything through by 2. So 2k plus k, because we've got k over 2, and I multiply it by 2, I'm just going to get k plus 2k over 3 plus, well, if I've got something like divided by 4 and I times it by 2, that's just going to leave me with k over 2. I'm going to multiply by 3. So 6k plus 3k plus 2k plus 3k over 2 equals 6. And then I'm going to multiply by 2 again. 12k plus 6k plus 4k plus 3k equals 12. So therefore 18, 19, 20, 22, 23, 25k is equal to 12. And 12 is equal, sorry, k is equal to 12 over 25. So we've used the fact that we know that this all sums to 1 to solve our value for k. So to give the probability distribution of x in table form, well, I've already done that in terms of k, but obviously it wants us to do that actually with numbers. So to save myself rewriting it out again, so probability of getting 1 will be 12 over 25. 12 over 25 divided by 2 will be 12 over 50. 12 over 25 divided by 3 will be 12 over 75. And 4 will be 12 over 100. If you're not sure if that's accurate, just go through in your calculator and check that it adds up to 1, which it does. So therefore, the likelihood is that I have actually done something, that I have done it right. because then if you'd done it wrong, it probably wouldn't add up to 1. So find the probability that x is greater than 2. Well, for the probability of x to be greater than 2, that means it must either be 3 or 4. So the probability that x is 3 plus the probability that x is 4. So that's 12 over 75 plus 12 over 100. We are not going to worry about doing fractions by hand. We're just going to type them into our calculator. 7 over 25. Find the probability that x is between 1 and 4. Well, that's the probability that x is equal to 2 plus the probability that x is equal to 3. So 12 over 50 plus 12 over 75. That we'll do on a calculator. Which is 2/5. Finally, the probability that x is greater than 4. Well, there's no option in our discrete random variable that it's greater than 4. So therefore, the probability is 0. We don't need to say 0 out of anything, 0 out of 100, 0 out of 25, whatever it is you want to look at. Just put 0. We don't need to write it as a fraction. So the next two examples on the next slide are examples that I've selected from the book because I think they're quite challenging examples. So they're not formal examples given to you. They're actually from the exercise that I just wanted to have a look at because they are more challenging. So example number 3. This spinner is spun until it lands on red or has been spun 4 times in total. So we have a spinner with 2 red sections and 3 blue sections. So although it doesn't state it, the implication in this question is that all 3 of these are equal size. So we do have to assume that in this case, otherwise it wouldn't be possible to do this question. So find the probability distribution of the random variable s, the number of times the spinner is spun. So this wants us to actually write up the table or the mass function, doesn't matter which, of all the probabilities. So the first thing we need to do is we need to actually write down our outcomes because S is the number of times the spinner is spun. So, if I spin my spinner only once, the outcome of that must be that I got a red. That's the only option it can be because either I stop when I've got a red or I spin it again until I get a red or until I've done it 4 times. So the probability of getting a red is 2/5. Okay, easy. For the spinner to have been spun twice, I must have got a blue first and then a red. That's the only possible outcome because if I get a red, I stop. If I get a blue, I carry on until I've spun it 4 times. So therefore the probability is 3/5 multiplied by 2/5, which is 6/25. For me to have spun it 3 times, I must have spun a blue, then another blue, and then a red, because I wouldn't have stopped after 3 if I didn't land on a red for the final time, and if I'd rolled a red before, then I would have stopped already. So that's 3/5 squared, because it's 3/5 times 3/5, times by 2/5, which is 18/125. Now 4 times you have to be careful. The likelihood is that you would put that you got 3 blues and then a red, which is not wrong. That is absolutely one of the options. And that is 54/625. But after 4 spins, I stop whether I've got a red or not. So it is possible that I got 4 blues, in which case the game has just ended, so I stop anyway, which is 3/5 to the power of 4, which should be 81/625. So because it wants the distribution, it wants to see it in either a table or it wants to see it in a mass function. I generally prefer doing a table. I'm not particularly sure why, I just do. So we've either got 1 spin, 2 spins, 3 spins, or 4 spins. So 1 spin is just a red, which is 2/5. 2 is blue then red, which is 6/25. 3 is blue, blue, red, which is 18/125. The last box is 54/625 plus 81/625, because both of those options are acceptable options, which simplifies to 27/125. So that is how you do that question. It's about being logical in your approach to your outcomes. So finally for this section, example 4, which is still on slide 4 on your PowerPoint. So a discrete random variable has a probability distribution shown in the table. So that I can actually be watching what I'm doing rather than keeping looking at the screen, I'm going to copy it down. So my possible outcomes are 0, 1 and 2. The probability of 0 is 1/4 minus A. The probability of 1 is A, and the probability of 2 is 1/2 plus A. Find the value of A. A reminder that these add up to 1. So we're going to expand these brackets. It's really important that I've put brackets around them. I've got a negative, so we don't forget that. Although because here we're adding it together, it's not so much of an issue. It can be an issue when we're doing other problems. From an examiner's point of view, which I did was last year, I marked pure paper 1. Brackets actually led to a significant number of students losing marks. So I am quite pedantic with brackets. So even though they're not the most necessary here, that is why I've put them in. So 3/4 plus A is equal to 1. Because we've got 1/4 plus 1/2, which gives me 3/4, minus A plus A plus A. Obviously subtract A and plus A cancel each other out. So you've got plus A here. So therefore A is equal to 1/4. If we're not sure, we can always check that it works. So this would make the probability of getting 0, 0. This would make the probability of getting 1, 1/4, and the probability of getting 2, 3/4. That adds up to 1, so perfect answer. I know I've gone into a lot of detail with this section, considering it's quite a small section. However, it's one that a lot of students kind of tend to forget about when they're revising. Where they consider binomial to be harder, they tend to revise binomial in more detail. And that does mean when they then come across these questions, these are the ones they end up actually more likely to get wrong. So it is really important that you are doing practice. Now on the PowerPoint, I have for later sections actually selected some examples for you to do. In this one, I think it's just worth you working through because it's looking in a range of different examples that these kind of questions could come up. Particularly looking at the E or the P questions, so the exam or the problem solving questions are really useful with this because it is one you might forget over time, so it's worth putting in the effort in.